how can we determine the best regression line for a set of data? And we're going to handle this by squaring the residuals. The regression line we want is the one that minimizes the squared residuals. Okay, so we can determine the best regression line for a set of data by squaring the residuals and then find the line that minimizes the squared residuals. Is the least squared regression line resistant to outliers? No, it is not. No. No, it'll still pull in that direction. So even though this doesn't ask for this, I'm going to give it to you anyhow. Okay, I'm going to give you the definition for a least squared regression line. Even though it's not on here, I'm going to go ahead and give it. So least squared regression line of y on x is a line that makes the sum of the squared residuals as small as possible. And that's going to be our best line for our set of data. Okay, now it's time to check your understanding. On page 171, stop, check your understanding. Okay, if you had trouble with this practice, you need to see either Miss Hines or myself to help you with the technology part of it. Okay, so here's a sprint time and jump time again. The data for the 13 students who ran the sprint and then competed in a long jump competition is in the table below. Calculate the equation for the least squares regression line using technology. I'm going to use the Inspire. Okay, I've already got this in, but I'm going to pretend I don't. So I'm going to here, do a new document and a spreadsheet, and up here I will type sprint time. Actually just sprint and jump for long jump, and then put this stuff in. Bear with me. Oops, wrong way. Okay, once we get that in, we are going to go ahead and graph this. So, make a page, statistics, and go down here, and we want this to be our sprint time. And over here, this will be our jump distance. And there you go. Okay, so if I want to calculate the equation of the line of least squares regression using technology, I'm going to go in here and I'm going to go to Menu and Analyze Regression. Alright, and we want A plus BX. And there's our line, and there is our equation. Okay? Okay, so interpret the slope in context. Well, for every sprint second, the long jump distance goes down by 27.6287 feet. Okay, so interpret the slope in context. Does it make sense to interpret the y-intercept? The slope is for every sprint second, the long jump distance goes down by 27.62 inches. Does it make sense to interpret the y-intercept, it really doesn't make sense because for x to be 0 would be there was no sprint time, and whoever was jumping would jump at 304 feet, 304 and a half feet really, and it's probably not possible, or at least not probable. So no, it really doesn't make sense to interpret that y-intercept. Okay, so next we're going to calculate and interpret the residual for a student who had a sprint time of 8:01 seconds. Okay, so the predicted value for the student, or the predicted distance for the student sprinting 8.01 seconds, would be found by substituting 0.801 in for our x. Okay, so to find to predict how long, to predict the length or the distance of the long jump of somebody running 8.01 seconds, we substitute 8.01 in for x, and we get 83.25. Now that's our predicted value. If I want to interpret the residual for that student, then I need to take the actual and subtract the predicted. Our actual was 71 at 8.01 seconds. We subtract our predicted, and we get a negative 12.25. So what does that mean? Well, that means that we predicted 12.25 feet higher than the actual. Our predicted is 12.25 inches farther than our actual. One of the reasons for giving the equation of the least squares regression line is we can give the equation in terms of the mean and standard deviation, actually the means and standard deviations of the two variables and their correlation. So, how can we calculate the least squares regression line from summary statistics? Okay, so how do we calculate the least squares regression line from the summary statistics? Well, remember that y hat is equal to a plus bx. The slope b is found by our correlation r multiplied by the standard deviation of y over the standard deviation of x. And our y-intercept, which is a, is equal to y mean minus the slope, or b, times the x mean. So what we'll need to do is we'll need to find the mean of x, the mean of y, the standard deviation of x, and the standard deviation of y, and their correlation r. So we can do that on our calculator. Okay, so go back to the table, and we're going to do menu, and then statistics, stat calculations, and I want linear regression, and that's going to be the sprint time for x, the jump distance for y. Okay, so now we got all the data here. Standard deviation of y. There's our mean. Our standard deviation of x. Our y mean. Standard deviation for y. And there is r. So, we're going to calculate it using this. And by the way, there's no set rule on where to round to, what decimal places to round to. There's no firm rule on that. Our advice, or my advice, would be to give your answer correct to 2 or 3 non-zero decimal places. The only exception for this is if you're using one of the tables in the back of the book and give the value shown in the table. So if it goes to 4 place values, then go to 4 place values, such as the table A. And yes, you will not you will not have to memorize these formulas. They will be on the formula sheet for the AP exam, so you don't have to worry about that. The correlation is the multiplier, and it determines whether it is positive or negative, whether the slope is positive or negative. Okay, so we're going to do this little example here. The number of miles in thousands for 11 used Hondas have the mean of 50.5 and the standard deviation of 19.3. The advertised prices had a mean of 14.425 and a standard deviation of 1,899. The correlation for these variables is a negative 0.874. Find the equation of the least squares regression. Explain what change in price would you expect for each additional 19.3 thousand miles. Okay, the first thing we're going to do is find the slope. Okay, so to find our slope, or B, we're going to take the R, correlation R, and multiply it by the standard deviation of Y over the standard deviation of X. Our correlation of R is a negative 0.874, and we're multiplying it by the standard deviation of Y, which was 1,899, over the standard deviation of X, which was 19.3. Okay, and that equals a negative 86.0. So the next thing we're going to do is to find our y-intercept. Okay, so to find A, we take the y-mean and we minus B times the x mean. So the y-mean was 14,425, and B was 86, and our x-mean is 50.5. And when we put those all together, our y-intercept is 18,768. Okay, so find the equation of the least squares regression and explain the change in price we would expect for each additional 19.3 miles. Every 19.3 thousand miles. So what this is saying is that for each additional 19.3 thousand miles, we expect the car to go down by negative, or by 0.874 times 18.9 by $1,899. Start that again. Okay, so what this means is that for every standard deviation, or for every 19.3 miles, we expect the price of the car to go down by 8.74 times 1,899. So, okay, so for every additional 19.3 thousand miles, we expect the cost to change by this amount. When we put the numbers in, we get a negative 1,660. So the CRV will cost about $1,660 less for each additional 19.3 thousand miles. Okay, so the CRV will cost about $1,660 less for each additional 19.3 thousand miles. The CRV will cost about $1,660 less for each additional 19.3 thousand miles. Thank God this is done.